So these are going to be SN1 substitution and E1 elimination. They frequently compete in the same reaction. Part A, propose the mechanism and predict the products for the solvolysis, solvolysis of 2-bromo-2,3,3 trimethylbutane in methanol. Okay, so your reactants here are going to be, well, you have this bromo-trimethylbutane, right? And so you have to write that out first. This is going to be SN1 and E1 reactions, and so that's always going to involve it breaking apart, right? And you won't have any attacker at the beginning because, again, SN1 means starts off by itself, right? No attacker. Also, you can know that because we only have methanol, right? Okay, so we're a lysis, right? What does lysis mean? It means some sort of breaking apart, doesn't it? Okay. And so we're expecting this to break apart with the solvent being involved in replacing something. Okay. Okay, so the first part of this is going to be, well, the Br minus coming off, right? We have our leaving group, leaves. And the leaving group has to be, well, Br. Okay, so the Br minus will come off. That will leave us with a carbocation. Okay. And we'll have Br minus as a product, right? So it's just floating there. Well, the next thing we do is we look for what will be our nucleophile. What could act as a nucleophile in this case? Well, we have solvolysis, right? Meaning your solvent. Solvent is methanol. So it's probably going to be methanol, right? That makes sense. So we look at methanol. It has some lone pairs on it. Those lone pairs are going to go into a bond with the carbocation. Notice that that's simply electronucleophile interaction, right? That same sort of thing we've seen all these. Okay, fantastic. So that's going to leave us with an O that has an H on it, doesn't it? See that? So if we make that new bond, don't forget, you never lose or gain electrons, right? They have to go somewhere, okay? So when we make that bond, that's going to give us this oxygen here. That was neutral. So it's going to now have a positive charge. And it's going to still have a hydrogen. And it's going to have 2 carbon bonds now, right? Okay. So you see how this now has this very unstable oxygen, right? Okay. Which has an acidic proton. Okay. So the next part is we're going to have some sort of what can act as a base to take that proton, which is very acidic now, right? Okay, and so our proton is going to be donated to another methanol, because that's the only thing that could act as a base in this case. Remember that the Br minus won't take on a proton, right? Because HBr would be a strong acid, it would lose the proton immediately.
Now, where's that? Is that going to the H or to the CH3? Not the other.
This one?
Yeah, because I see it looks like a dotted line.
That's the dotted line. So the electrons here, this lone pair, are going into a bond with this hydrogen, the acidic hydrogen. And this oxygen is becoming protonated. And then the electrons that were in this oxygen-hydrogen bond before are going to go to the oxygen and give it a lone pair. So it now is normal oxygen, right? Not positive oxygen. Okay, not a cation oxygen. So this is what you end up with. You now have this oxygen, oxygen CH3 group, excuse me. And this one right here is going to be the OH2 plus off of the methyl. Did you have any questions about that, or did you get lost anywhere?
So, this is like a really basic question, but when you are moving when you're taking something, you put the arrow to what you're taking, right? It's like indicating that you're taking that H. Or
Okay, so not the other way. When you always put arrows moving electrons. So you're moving electrons from here into a bond with that H. So that H is gaining access to those electrons through what is called a coordinate covalent bond, actually. And these electrons that are in this bond, hey, she's not alone. These electrons that are in this bond are going onto that oxygen there, which had a positive charge.
I don't know, there was like one time, maybe, I don't know, there was like an arrow.
The arrows always show you where the electrons are moving. That's it. Yep. They never show you anything else. It's always where are electrons moving. And so you always follow electrons in organic chemistry. And the one-sided arrow shows you where one electron goes. Okay. Did you want to do B?
Yeah.
Okay. Compare the function of solvent, methanol, in the E1 and SN1 reactions. So in the E1 reaction, the solvent, methanol in this case, serves two functions. One, it blank the ionization process by solvating both the leaving group, bromide, and the carbocation, and then we go on to the next one. So we do the first one first. So it does what? It's not going to hinder, right? Has to help in some way. Base doesn't make any sense there. Double doesn't make any sense. E1 doesn't make any sense. Oxygen doesn't make any sense. Carbon doesn't make any sense. Triple, SN2, none of those other ones make sense, right? It can only be aids or hinders. Has to be aids, right? Because it solvates both the leaving group, making it easier to leave, right? And the carbocation, making that easier to mix and react with things. So, has to be some form of aiding, right? It would have negative language if it hindered it. That's actually kind of an English question, isn't it? Can you understand positive and negative in English language? Maybe not. It serves as an what? To remove the proton from a carbon adjacent to the carbocation to form the carbon-carbon what bond? Okay, so we're removing a proton. If you accept a donated proton, you are a what? Base. So the things that would work there would be acid and base, right? Okay, and we're a base because we're accepting a proton. So again, you don't actually need to know anything but acid base there, do you? We're going to form a carbon-carbon what bond? Well, we're doing an E1 reaction, so we have to form a what bond between carbon-carbon? A double. Because that's E1 reactions, right? Okay. That's all elimination reactions. All right. So the SN1 mechanism adds a third function to the solvent. And the first step is the same as in what? As in blank. Ionization to form the carbocation. Well, that sounds exactly like up here, doesn't it? Mm-hmm. And what was that? Yeah, the E1, right? Okay. SN2 wouldn't make any sense, would it? Because SN2 requires an attack. The first step at breaking apart on its own means it has to be some form of 1, right? Okay, the second step, blah, blah, blah. The third step, blah, blah, blah. Okay. The third step involves the solvent acting like a base and removing a proton, although from an blank atom. My screen is really dirty. Wow, that looked like a period. Atom, SN1, and not a blank atom. Okay, so we have our third step, right? At this point, we've replaced what's on there, right? So we're not doing the E1. We're not losing a proton to make a double bond, are we? So, and it literally is saying that, right? The third steps, although from, means it's probably not the same as the E1, right? So in the E1, we remove the hydrogen, that acidic hydrogen from a carbon, right? And we made that carbon-carbon double bond, okay? So if it's the other than that, not that, has to be the other option, which is oxygen, right? And then not a, well then that would be the carbon bond, right? For the E1. Wow, this is like straight up. This reminds me of an ACT question, right? Or a TOEFL question where they're testing your English comprehension. Yeah, it literally, if you just read the English and understand nuance in English, you can answer all these questions directly. You need very little chemistry knowledge. That's a, Okay. Anyways, did anybody miss out on anything? Didn't understand anything? Got lost in anything? No? Okay. Fantastic. All right, I will stop recording.